Well, thanks a lot to the organizers for the opportunity of being here. This is really a great meeting, and I'm enjoying it a lot. Mostly about superconductivity, and I have had a good chance of collaborating with a number of very good people, which are listed here. And let me start by stressing, as other people have done already, that there are significant differences between typical strongly correlated systems and twisted graphene and related systems, in the sense that, especially in twisted bilayer graphene near the first magic angle, superconductivity is very prevalent, much more than what you find in the Nick ties or the cuprates. And then you can explain, in most of the strongly correlated systems, the superconductivity can be explained in terms of as mediated by fluctuations associated to magnetic phases, typically. In addition, the flat bands in the twisted bilayer graphene have nothing to do with the flat bands you see in the cuprates or the heavy fermion systems, because there these flat bands are based on very localized atomic orbitals which are separated, and then they become even flatter because of interactions. And in twisted bilayer graphene, you have flat bands in the absence of interactions, and moreover, interactions go in the opposite way. And let me just mention that, as also remarked here, interaction effects in carbon compounds were rare. Let me only say that renormalization plays a role in carbon compounds, nevertheless, because it was observed experimentally, this very strong renormalization of the Fermi velocity near the Dirac point in very clean suspended samples. And here there is a kind of scaling, it's a classification of interactions in twisted bilayer graphene. Twisted bilayer graphene has a large number associated to it, which is the number of sites in the Moiré unit cell, which is about 10,000, and that allows you for a neat classification of things in terms of this number n. And by far, what you can tell, and is consistent with what everybody else has obtained, is the long-range Coulomb interaction is the most important in coupling among electrons in such a system. And because of that, when you turn on the interaction and you do straightforward Hartree calculations, you get huge deformations of the band structure. The deformation, even if you start with complete flat bands, they are there in the chiral limit. And moreover, if you look at it, you have like a flat band moving up and down at the K and M points, while at the gamma point, the bands don't change very much, which is actually is coming from the significant changes in the wave functions in the flat bands as you go from gamma to K, and that's also consistent with ideas put forward by Andrei Bernev here about the topological Kondo system. It seems like in these systems you have the coexistence of dispersive and localized orbitals very clearly. This is a kind of animation of what happens as you change the filling. It was done for a different situation, but as you see, the bands are not that narrow, except when you go to have filling, which is what is going to happen now. Then is when you have the real narrow bands predicted by Bistritzer and McDonald, and then you will get, again, dispersive bands as you turn on, as you induce more and more carriers into the conduction band. And this thing has been confirmed in many theoretical calculations and also by experiments. And then, in addition, you can go beyond the Hartree calculation I have showed to you, and you can put the Fock term, the exchange term, and then you can look for broken symmetry phases, and there are plenty. There are many polarized phases, polarized in value or spin. Problem is that these things, which are consistent with the so-called cascade observed experimentally by STM and by compressibility measurements, this cascade can be explained in terms of polarized phase you can get from Hartree-Fock. The only problem is that the many phases, broken symmetry phases, Hartree-Fock gives you, are very close in energy, and to distinguish them is not that trivial, but that's a different issue. So putting all together, one can say that Hartree-Fock calculations give a reasonable picture of many of the features of twisted bilayer graphene near the first magic angle. But that's not what I would like to talk about. I want to talk about superconductivity. And before that, let me mention a very nice model for superconductivity emerging from the passive interactions put forward by Valentin Kreppel and Liang Fu, and with whom we collaborated later. And it's just as simple as it can get if you want to get superconductivity out of repassive interactions. You have electrons in the honeycomb lattice, spinless electrons in the honeycomb lattice. The two sublattices have different lattice potentials, and you only have fillings. So there is one sublattice which is basically filled with electrons, and you start adding carriers to the other sublattice. And then you only put the simplest interaction you can imagine, which is a repulsive interaction between nearest neighbors. I mean, the electrons are spinless, so a Hubbard interaction cannot exist. But so you just include this kind of interaction. By the way, this kind of models, my colleague Misha Garnerson mentioned to me that they were considered in the former Soviet Union way back. But in any case, what happens, and this is almost hand-waving, what was shown by Valentin Kreppel and Liang Fu is that, I mean, in order for an electron to move in this lattice, it needs to displace, I mean, you only have nearest neighbor hoppings, so it has to displace electrons which are sitting comfortably in the low energy sublattice. And because of that, you have to pay a price in energy, and you have like an effective hopping, which is inversely proportional to the difference in the sublattice energies. Now, if you have two electrons moving around, and then you have one electron fixed, which is the one, here, this one is fixed, it doesn't move. If you look at how the energy cost in order for the other electron to move, it's lower. The existence of one electron allows another electron in its proximity to move more easily, because the intermediate states, which are high energy states you have to go through, have lower energy. So because of that, you have created an extra interaction, which is like an electron-assisted term, and that thing immediately leads to superconductivity. So our contribution was to put this scheme in more formal grounds, to look at the kind of superconductivity you have, and what you get is a kind of F-wave superconductivity. It's a system which have pockets at the K and K prime points of the Brillouin zone, and you have a superconductivity which, as induced by a repulsive interaction, has different signs in different pockets, but there is a full gap within each pocket. And the reason for that is when you screen the interaction, you create new interactions, which are, I mean, at first you have only interactions between electrons in different sublattices. You screen the interactions, and you have interactions between electrons in the same sublattice, long-range interactions. And because of it's due to screening, these kinds of diagrams are attractive, and they overcome the bare repulsive interaction you started from, and that gives you superconductivity. And I would like to make the point that this is interesting because it's somehow related to what happens in the cuprates near the first magic angle. And in order to, and I have already mentioned F-wave superconductivity, that's a very natural thing to have in a system with repulsive interactions. As soon as you have two valleys, if the intra-valley repulsion is smaller than the inter-valley repulsion, you will always get superconductivity, and that's a very simplified model of the cuprates. You get D-wave superconductivity in the cuprates as soon as you have two big Van Hoff singularities in the Brillouin zone of the cuprate, and as soon as the intra-Van Hoff singularity, even if it's repulsive, is weaker than the inter-Van Hoff singularity, you will get a D-wave superconductivity. Well, this is the famous Uemura plot already mentioned, and the carbon compounds are listed here, and there is a clear difference between twisted bilayer graphene and symmetric tri-layers or 4 layers, and the rest of the carbon compounds. So this is relatively higher in twisted bilayer graphene, much more than in the untwisted systems. And now I'm going to talk seriously about superconductivity. I mean, there are many works, very interesting ones, related to superconductivity. Here I'm listing a few of them, especially the early ones where many mechanisms have been proposed. I will discuss mostly sorry, here at the bottom, the superconductivity out of electron-electron interactions, and you make the calculations using diagrammatic methods, Kohn-Latinger-like, and these calculations and a bit more stuff is included in all these references, and I will go through them right now. So all started with the seminal work by Walter Kohn and Joachim Luttinger. They were studying superconductivity because of repulsive interactions. They noticed that a Fermi surface leads to Friedel oscillations, and Friedel oscillations lead to effective interactions which are attractive somewhere, and then they said, well, maybe one can accommodate a Cooper pair in the attractive regions created by the screen interaction, and then one will get superconductivity. And let me mention that there are different diagrams. These are the diagrams Kohn and Luttinger studied. They are second-order perturbative diagrams in the interaction. And we are going to look basically to the diagram here with the red signal on top of it, because reasons I try to explain. And as Kohn and Luttinger mentioned, if you study this diagram, then you have to worry about longitudinal acoustic phonons as well, because this diagram, this RPA bubble, implies you're looking at electron-hole charge fluctuations. And a charge fluctuation can couple through the deformation potential to longitudinal acoustic phonons. So the calculations I'm going to report it not only includes electron-electron interactions, it also includes, by definition, LA phonons, because they are unavoidable if you start from this point of view. Let me say that Walter Kohn and Joachim Luttinger were unlucky because they were looking for superconductivity in the worst possible situation, the three-dimensional electron gas. If they had applied their same diagrammatic techniques to a very anisotropic system like the cuprates, immediately they would have found superconductivity for the same reasons and using the same diagrams. And this is another paper from way back on graphene near Van Hoff singularity. I mean, if you apply these diagrammatic techniques to the right system, they will show up that you will get superconductivity in a very straightforward way. And then, in addition, what happens in the cuprates is that you have in the same region of parameter space electron-hole pairs, plasmons, and phonons. They are all sitting together. And if you compare what happens, this is a kind of cartoon of twisted bilayer graphene, and this is a more conventional two-dimensional electron gas. The phonons are well below the region occupied by the electron-hole pairs and the plasmons, while in twisted bilayer graphene, they are all together. They are all mixed. This is a famous calculation by Leonid Levitov and Cyprian Lewandowski. And this is these are the excitations we're going to deal with. Electron-hole pairs, plasmons, and longitudinal phonons. And this is the kind of calculation we do. We linearize this. We assume there is, we write down the effective interaction, which includes the bare Coulomb interaction plus screening to all orders. So we do not consider only this diagram. We consider this diagram and all other possible bubbles, the full RPA chain. And we linearize the gap equation. We go close to TC, and we solve for possible order, superconducting order parameters one can get out of this interaction. And let me also emphasize that in graphene, as we know, there are 4 flavors, spin and valley. So the RPA bubbles come with a factor of 4. They can have any flavor flowing through the diagram, while the other diagrams are less important. So this is like a 1/n expansion, similar to the 1/n expansion people do in quantum chromodynamics. The only thing is that in quantum chromodynamics, n is 3. And this is a kind of formal thing how we solve the problem. And we did find, we first tried TBG, twisted bilayer graphene, and we found superconductivity of the F-type, similar to the superconductivity I mentioned before for this toy model invented by Krepper and Fu, with relatively large critical temperatures in the order of 1 to 5 Kelvin. Let me stress that you shouldn't trust too much a single calculation of a critical temperature. I'm a theorist and I know it well. So we were looking for trends rather than particular values. The fact that we get 2 or 3 Kelvin is good for us, but we didn't give a lot of relevance to it. But this kind of mechanism gives sizable, let me put it that way, in the right range of parameters, critical temperature. The phonons play a role, even if the bare interaction is repulsive and we don't put any attractive interaction. The phonons are only there coupling charge fluctuations to charge fluctuations. The phonons play a role. If you switch them off, the critical temperature goes down by much, and that is in part associated to the very existence of the Moiré. When you couple two phonons, you don't not only couple two phonons which connect 2 points in the Fermi surface of the Moiré, there are also unclad phonons which have extra reciprocal lattice vectors in the wavelength, and they also play a role. So the electron-phonon coupling is enhanced because of that. And these are more results. There is a peak always in these results at zero filling. That's because we were not doing a self-consistent Hartree-Fock calculation at the time, because otherwise that peak will disappear because the Hartree-Fock will open it up. So, but typically the superconductivity correlates well with the with the electron density at the Fermi level. There were previous calculations neglecting the phonons, and they are consistent with our results. There, your TC, if you only keep electron and electron interactions, you also have superconductivity, but the TC drops by an order of magnitude. These are more details of how we were calculating things. At the end of the day, I repeat, for TBG, we get F-wave superconductivity with a full gap in each pocket. There are things we miss, because, for instance, we use the static dielectric function for computational, because of computational limitations, so that puts limits on the validity of these results. I mean, we cannot go to high temperatures because then things like the frequency dependence of the screening will be important and no retardation effects. And we don't have other types of phonons, for instance, like optical phonons or TA transverse acoustic phonons. But the results for this kind of coupling through charge fluctuations only are pretty robust, and you get definitely superconductivity. The calculations can be applied also to polarized phases, provided that the two values exist. So a spin polarized phase will can be solved in the same way. The only thing is that instead of 4 flavors, you will have 2. Then you know that superconductivity was found in symmetric trilayers by a number of people, so we repeated our calculations for symmetric trilayers, and it was shown. As it was shown that symmetric trilayers are basically a monolayer plus a bilayer, we got superconductivity similar to the one we found for twisted bilayer graphene, same order of magnitude and everything. Now we went, there was the discovery of superconductivity in untwisted systems, so we repeated our calculation in the same manner, and we got also superconductivity, but quite of a different character. The superconductivity here is, I mean, we included everything in the same way, phonons, electron-electron interactions, and so forth. The superconductivity occurs at much lower temperatures, and in addition, the gap has nodes within each pocket. So that is more what you expect in a conventional, strongly correlated system. And moreover, we played with Ising spin orbit coupling, and we found that the Ising spin orbit coupling enhanced significantly the critical temperature, which is also consistent with experiments. That thing is easy to explain because you have this repulsive potential in Fourier space. You Fourier transform it, and because of the fact that as function of Q is more repulsive at large Q than at small q, you have in real space a potential which has attractive regions. And then when you apply the Zeeman spin-orbit coupling, you lose two values. So the screening is weaker. And then the repulsive potential is stronger. And when you Fourier transform it, the negative minima are also deeper. So that is a good justification for why you get a higher critical temperature when you lose values because of the Zeeman spin-orbit coupling. And then there is a very simple limit when you only have, you screen perfectly the intra-valley couplings, and you only have inter-valley repulsive interactions, and then you go again to F-wave superconductivity for the reasons I explained before. Then we went to more than two layers, to 4 layers and so on. Again, the superconductivity is of the second type. It has nodes and low critical temperatures. And the last thing we did was to look at a twisted double bilayer, which is a system very similar to a twisted bilayer. And in order to be sure what we were doing made sense, we interpolated and what we did was, we are theorists after all, we had a twisted bilayer with 2 layers, one above the other below, and we tuned the coupling between within each bilayer. So we could interpolate between a twisted bilayer and a twisted double bilayer. And what happens with the critical temperature is that it drops very quickly as soon as you as you start coupling the first and the fourth layer to the twisted bilayer. There's a big change in critical temperature, which also follows a big change in the shape of the bands induced by interactions, which is no longer there. And in a way, I think Andrei Bernal knows that well. It is the famous topological condom model that doesn't apply to a twisted bilayer. So you need something with a combination of dispersive and flat bands in order to get the superconductivity you find in a twisted bilayer. And we repeated the situation for a helical trilayer, and again in a helical trilayer, you don't get strong superconductivity. So this is a kind of summary of what we are getting. You need the phonons, you need electron-electron interaction, and you need these umclap processes as well, both in the electron-electron coupling and in the electron-phonon coupling. You have used always the same set of parameters for all the systems, and these parameters existed before twisted bilayers and so on. They are well known for graphene work. So I think the trend we get for the superconductivity is quite reasonable. Of course, when we get, very, very low critical temperatures, it means that this mechanism is very weak, and then any other mechanism may change things significantly. That cannot be ruled out, but at least the fact that there is a big difference between twisted bilayer graphene and the other superconductors is there. So here just I wanted to point out that we are missing precisely this exciton-like diagram for computing problems. Sooner or later we will make it. So we're leaving a lot of things out. Nevertheless, we think that this kind of starting point, this metallic starting point, can be reasonable, which is consistent with the dynamical beam field calculations already done. But then these two papers were posted not long ago, and Philip Kim described them very well. And they imply that there are also a lot of low energy excitations in the superconductivity of a twisted bilayer. We think that it may be due to pair breaking effects. If you have disorder, any type of disorder, that will, in the case of the F-wave superconductor I have described to you, elastic disorder played exactly the same role as magnetic impurities in an S-wave superconductor. And that can change a lot the type of superconductivity you observe. But in order to make them be more quantitative, you need things like the mean free path and stuff like that, which are not very available. It was discussed yesterday. And let me also mention that if you have an F-wave superconductor, it's a non-trivial superconductor. It's not S-wave. And because of that, for instance, you cannot have Andreev backscattering in the contact regime in STM experiment. That was discussed in this nice paper after experiments by Ali Yazdani. But you can have something else. If you have an F-wave superconductor and you come with a tip close to it, the tip can induce transitions from valley to valley. The tip is also scalar perturbation. And that will create extra Andreev states inside the gap. And then if you add those extra Andreev states, you can have peaks which resemble Andreev scattering, but that's because of what happens, because the tip itself is perturbing the superconducting phase. And so these are the experiments I was mentioning to you, STM experiments, according to which you see peaks in the contact regime in STM experiments. And if last but not least, let me mention that if you have this kind of wave superconductivity, you can also have Majoranas not very protected, that's also true, because of the symmetries of the system. If you have an edge where an electron comes from one valley and is scattered back into the other valley, it's like what I mentioned to you that the tip can do. You have intervalley scattering and you have Majoranas, which can be sitting at corners of a flake and things like that. And that's it. Thanks a lot for your attention. Oh, yeah.
Thank you so much. Thank you for this nice talk. So you mentioned, maybe I didn't catch that in the tri-layer, you also find S-wave superconductivity. Is that
F-wave, yeah.
So how do you explain then, in our experiment and others, there is a huge breaking of the Pauli limit, like by a factor of 10?
Oh, because it's a good point. Yeah, F-wave means valley singlet spin triplet. It's a spin triplet superconductivity. Sorry, I didn't mention that.
Laura.
Can you explain again how you included the phonons? I think I didn't get it. Are they just added to the bare interaction, the electron-phonon mediated one?
Okay.
Are they included dynamically?
Maybe I should have plotted some better. Sorry for that. Yeah. We start with a bare Coulomb repulsion. Let me see, what is the Kohn-Lattinger scheme? Yeah, here. Here you see the Kohn-Lattinger scheme here. This is not the only diagram we have. We have many bubbles connected to bubbles, and then connected to the other Green's function. Now, between bubbles, we inserted also phonons, longitudinal acoustic phonons, because an electron-hole pair can decay into an LA phonon and, in addition, induce another electron-hole pair. So the initial interaction is always repulsive, and phonons only renormalize the propagation of these charge fluctuations. But if you kill the electric charge, for instance, you kill the superconductivity. So in order to have superconductivity of this type, you need a repulsive interaction to start from.
And then do you get the dynamic interaction?
No, because of, as I said, computational limitations. That implies, the fact that we're using a static dielectric function implies that you cannot trust calculate. If we had obtained a critical temperature comparable to the bandwidth, that could not be reliable. The reason being is that you need to include frequency retardation effects in the effective interaction. But as we get a critical temperature, which is definitely much lower than 1 MeV, and it's much lower than the bandwidth, I think the static approximation to the dielectric function is more or less justified.
Thanks.
Yeah, so I think I want to re-ask the question I asked Shankar yesterday. This kind of calculation, are you working in the correct normal state for TBLG or TTG?
The correct, no, for TMD.
No, for TBLG or TTG.
Could you repeat?
Twisted bilayer or twisted trilayer?
as opposed to the Moiré-less systems? Because the normal state is very different, right?
Twisted, sorry. I'm not sure I understood you.
Can you repeat the question from the beginning?
So whether you are considering the fact that you may have twisted parallel grouping multi-channel or untwisted or tri-layer, all these cases.
Yeah, we have considered, sorry, yeah,
maybe I can restate my question, right?
Sorry, yeah. No,
there's Moiré-less superconductivity in
what we have considered is in this table. So you see this table here? These are the cases we have considered. There are few of them are twisted and others are not twisted.
Yeah, okay. So but phenomenologically, the normal state in the twisted systems, let's take twisted bilayer graphene, the charge carrier density is not the band structure carrier density. It's very small. It's a deviation from the correlated insulator. And that change happens at very high temperature, much above TC.
Okay.
So then what's the justification for this kind of approach? Same question I asked Shankar yesterday.
For the change, no, good.
For not taking the broken symmetries.
What was giving you the low charge?
First, you can get the cascade. Okay, good point. First, you can get the cascade just by renormalizing the quasi-particle weight. That is the result of the renormalization calculations done by Lenny Vascones and also by Roser and Andre. Second, if you have a spin polarized phase, the whole thing will work as well. What we have not considered is a valley polarized situation.
We know what the broken symmetry is, right? It's this IKS or whatever. That's a very specific state. And, but it's not so much about the quasi-particle weight. We know the charge density. It's not the full charge density. Right?
That's what I'm saying, because we just sweep the Fermi energy, and then the charge density is following. We look at different values of the chemical potential, and we make the calculation for that chemical potential. And whatever density is determined by the chemical potential is the one we use.
But if you don't have broken symmetry, it will capture the full density of whatever you put in the flat bands. It doesn't calculate the density it refers to the insulating state. It's not. Okay. Good, but we find a broad range of densities where we have superconductivity. So then, if you have the density, I think we will still get superconductivity in the same ballpark. Maybe lower, if you have lower density, maybe lower critical temperature.
Could I just comment on it? Because the answer is yes or no. Senthil, the answer is no. Okay? The effects you are talking about are not included in this calculation, because that will make it computationally impossible. There is, miscommunication going on here, okay?
No, I understand the effects going through. The question is, why is that justified?
Okay, but that's as
justified as what I told you yesterday. It's not justified.
No, I asked you this.
Yeah, and I said it is justified by, convenience, what one can do, because these are very difficult calculations. Yeah.
But if I divide the density by 2, assuming there is a spin polarized phase, I think I will get superconductivity in the same ballpark. Lower critical temperature, but it will not go away.
But it's not a factor of 2, right? You're filling 2 plus epsilon. The charge density is epsilon. It's not a factor of 2.
But we're assuming that this is weak coupling superconductivity in the sense that you have some Fermi surface which emerges from a relatively wide band with respect to the superconducting gap and the critical temperature. So in that sense, this is a mean field calculation based on BCS theory, and the starting point needs to be a metal with 2 values, because we are not considering this momentum, Cooper pairs with finite momentum, which may emerge in a quarter metal. But if you believe you start from a metal, then the Umklapp processes which help the superconductivity in twisted bilayer graphene, they will be there as well. So
Okay.
I think that will not be a significant change. It will be a change within the errors to be expected in a calculation like this, because as I said, you cannot trust the absolute value of the critical temperature. You can say, well, this is going to be of this order of magnitude, but not more.
Okay. Is there any other question? Maybe we can continue this discussion later.
So I have a maybe a bit strange question. If you can take this mechanism that you explore through all these materials and come up with a scenario by which it would be perfect, we give a really high TC over a really long range, how would that material look like? What should we look for?
That's a good point. I think twisted bilayer graphene at the first magic angle is very unique. You can cook up similarities to twisted bilayer graphene if you couple the two valleys by a substrate like silicon carbide, things like that. But the combination of unclap processes and so on, which really is helping the superconductivity, I think you only find it in twisted bilayer graphene. As I said, you have a double bilayer and it's gone. And it seems a very similar situation. But then you get a very, very small critical temperature because all these unclap processes, all this combination of dispersive and local bands are gone. They're no longer there.
So if this calculation is done for sodium metal, you're going to get a superconductivity of 5 kilo. This very calculation.
You are going to?
You get a superconducting piece of the order of 5 kilo. This was done by Liu Shan a long time ago, you know the answer. So that's what you get, because basically your RPA bubbles will...
No, but this is the Kohn-Latinger problem.
No.
They were looking to...
RPA bubbles there. RPA bubbles are a plasma. So the plasma mediated interaction will be there. You are imposing your main effect, trust me, your main effect is fine. Kohn-Latinger will give you a nanokelvin TC. It's the plasma that's giving you a TC of the order of a kelvin.
I don't think this calculation you're mentioning for a 3D electron gas like sodium will change very much the predictions of Kohn. You're saying that the predictions of Kohn and Latinger were underestimating...
You're mixing all of this. You have put infinite bubbles, infinite number of bubbles. So,
okay, this is...
what you have done, then you have made a static approximation.
Good
so
point.
That is another error in terms of Feynman diagrams. So this problem is not showing up. All I'm saying is you do it right.
Okay, so within 1 month we will have done it. Thank you.
So thank you very much, Paco. I wanted to ask about the screening effects, right? So the screening effects, because one can test a lot these Latinger-Kohn mechanism, in fact, by thinking about the role of screening effects, because you change the long range. So have you looked into that? If you compare them to experiments, because you can manipulate that with your parameters, of course, the range of screening that will change. Let's say if I think about the experiments where they can manipulate the distance to the leads.
We put always the gate at some distance, which is not too far. Having said that, I know of 2 very recent papers which are not posted yet, according to which if you use substrates with a high dielectric constant, you kill the superconductivity.
Okay. So
these papers are already floating around, and sooner or later they will appear.
Okay, yeah, that's a good point.
Okay. Any last question? If not, thank you, Paco, so much.